Now, there are going to be several different notations that get used anytime we're talking about derivatives. For example, we've been putting our focus on function notation for the majority of this. So when it comes to function notation, a simple prime will be good enough to represent a derivative. But all of these are derivatives, or more importantly, first-order derivatives. Now, the notation that gets used here, when we were talking about an average rate of change, we referred to that as delta y over delta x. As soon as we take the limit as h goes to 0, the value becomes what we call infinitesimal. Anytime you see a dy or a dx, that is referring to something infinitesimal. If infinite is big, infinitesimal is the same concept but small. Additionally, the use of d over dx means that I'm about to take the derivative of this thing with respect to the variable x. We could also say df over dx, or d over dx of f of x. The d notation is attributed to Gottfried Leibniz, widely accepted as one of the two fathers of differential calculus, the other being Sir Isaac Newton. Sir Isaac Newton is the one who came up with the prime notation. I typically find that to be a favorite among students. There are some other notations that get used, not necessarily in this class, but perhaps in other classes as well. A capital D can represent the derivative of a function, or a capital D with a subscript indicating the variable is also used for this. Additionally, we also have flyspeck notation. Flyspeck notation puts a number of dots above your dependent variable equivalent to the number of derivatives that it would like you to take. Now, many of these will have corresponding notations once we start taking derivatives of derivatives, which is what we should discuss now. So these are higher derivatives or higher order derivatives. It's what happens when you take the derivative of something. Now, with that in mind, the way that this extends is if you're interested in taking the derivative of something, f prime of x, this would be the limit as h approaches 0 of the difference quotient for f. If you're interested in a higher order derivative, in the prime notation, simply keep adding additional primes and apply the difference quotient to whatever function you're currently dealing with. Now, in the Leibniz notation, which gets used pretty frequently, a second derivative is saying take the derivative with respect to x of the derivative of y with respect to x. Please note that in the numerator there are now two d's. To shorthand this, we use d squared y. In the denominator you see two dx's, so the shorthand notation that gets used for this is dx squared. So d squared y over dx squared represents the second derivative. For a third order derivative, in the prime notation, just keep adding in primes. In the Leibniz notation, we would be taking the derivative of the second derivative of y with respect to x. So d cubed y over dx cubed. Now, as soon as you get to a fourth order derivative, the primes kind of break down. Even Sir Isaac Newton had his limits. His limits, get it? And said, once you get up to a fourth order derivative, I don't feel like counting all of those primes. So we'll just use a number to indicate what derivative we're on. More generally, if you're looking for an nth order derivative where n can represent any positive integer, the notation that gets used for this is the nth derivative of f with respect to x, or d to the n y over dx to the n. That would be your general nth order derivative.